now that I have basically learned how to, at least in principle, distribute different users to my space, how do I isolate my transmit and receive paths? I don't know how many of you played with walkie-talkies early on in your life, but when I was playing, at least with walkie-talkies, there was a very simple way to do that. You were holding your walkie-talkie and you had a button. So you click on this thing, you speak, so that means that the channel is now owned by the transmitter. You release that, that means now the channel is owned by the receiver. So this type of idea is great, but it's not a full duplex, meaning you can't speak and you can't listen at the same time. So obviously today we have found far better ways to deal with that. You don't have to push a button to your phone to talk, right? And if somebody interrupts you, will listen to that. So let's see how you might be able to do this. Again, there are two fundamental ideas here. One is to multiplex people based on frequency, and the other is to multiplex them based on time. So let me first talk a little bit about multiplexing based on frequency. What essentially that means is that you are speaking through your transmitter, you're listening through your receiver. Your diplexer is essentially dividing somehow, in this case based on frequency, how your antenna will be shared between transmitter and receiver. And you dedicate some frequency to your uplink, meaning where you're transmitting, and some frequency to your downlink, meaning when you're listening. That's a very simple idea, and in fact it's implemented in many, many systems today. And it has a few advantages and a few drawbacks. So the first thing that I would like to mention is maybe the main advantage of that system is that because basically transmitter has its own frequency and the receiver has its own frequency, you don't have to worry too much about accidental emissions. So that means that my receiver is locked to listen at this frequency. All other transmitters will be away from that, and that means that no accidental emissions will occur there. My receive channel is guaranteed or quasi-guaranteed to basically be quiet. So that means the noise there is under control, and I can actually design a pretty good receiver and a pretty good sensitivity for that. Probably the biggest drawback is leakage. What I mean by leakage is the following. So this transmitter is basically transmitting now, and you're also trying to receive now. The only difference is that there are two different frequencies, two different channels. But how much are they transmitting? Let's take the GSM, for example. In GSM, you may be transmitting 0 dBm here. Actually, sorry, this is pretty low, 30 dBm I meant, 1 watt. And you may be having to detect the signal, as I mentioned before, negative 100 dBm. How much is the difference between these two numbers? Doesn't take much, 130 dBs. So for the transmitter to be totally isolated from the receiver, you have to ensure an attenuation of 130 dB. So those of you who have ever tried to design a filter that has a rejection of 130 dB, you're probably saying that's quite impossible, and in fact, indeed, it is impossible. So the biggest problem that we have here is that the isolation between transmitter and receiver is not perfect. There's a significant leakage, and usually that leakage is in the order of 50 to 60 dBs. That means I can only guarantee an isolation of 50 or 60 dBs, and then you're going to have to deal with a pretty strong signal that comes from the transmitter. Of course, you're still in different bands. The transmitter is not in the same band as the receiver, but essentially the fact that you have a very, very strong signal, so let's put it like this, and even that figure doesn't do justice. So this is the receiving power. This is the transmitting power, even after the 50 or 60 dB. The fact that you have this giant thread right next to you basically puts a pretty high linearity requirements on the receiver. That means that when the receiver sees both of these signals are its input, it better be able to say that this is in one frequency and this is in another frequency. That's what I mean by linearity requirements. If it somehow starts mixing these two up, then guess what? Basically, the system doesn't work anymore. So linearity and leakage basically are the two biggest drawbacks when you're basically trying to separate the transmitter from the receiver based on frequency ideas. Now, you may say, why can't you just make a better filter? Right? So here is an example, actually, of a very good duplexer. that I just got from the market. It's based on acoustic filters. Towards the end of the class, we'll talk a little bit about this. What was interesting to notice here is that if you look at, for example, the receiving band, and if you look at how much isolation it has in the transmitter band, as I mentioned to you right now, is about 60 dB, and this is about state of the art. This is as good as it gets. What do you have to do to make this thing even higher? Well, lots of things, but one of the things that you have to do is penalize here the loss of the filter or the insertion loss. Penalizing the insertion loss is very, very bad because putting more loss on the receiver filter, it basically means you're diminishing its range, as we're going to learn later on. So it means you want to improve the leakage. That means that your receiver now can listen at shorter distances. So everything is interlinked, and without going into more detail, I just want you to give you that word of caution. The other way you can basically do this system is by simply separating things in time. Since it's so hard to listen and transmit at the same time based on different frequency bands, why can't you just shut the transmitter off? So now you say my transmitter works, now it doesn't. And indeed we do that with a simple switch. So the antenna basically transmits when it's connected to the transmitter, it receives when it's connected to the receiver. So essentially now we don't have dedicated frequency bands, we rather have dedicated time slots. So we basically change uplink and downlink based on different times. So as you can imagine here, we're basically solving many of the issues. So the leakage issue is not there anymore. I mean, what do you mean by leakage? This thing is off. And so the system is actually far simpler to do. The receiver actually is forgiving. It's also lower cost because part of the cost that we have to deal with is actually the filter I was mentioning before. Those filters are relatively expensive. They're bulky. And here, there's actually no need to use them. And so the system eventually will end up being lower cost from that perspective. But again, nothing is free. There are some drawbacks. Probably the biggest drawback is that you're not alone. And here's what I mean by that. Yes, at time slot 2, you're listening, but the rest of the world doesn't simply shut down just because you're trying to listen. So neighboring transmitters will actually still transmit. And because you don't have your own dedicated band, you're actually listening over the entire spectrum, you can't permit people from transmitting in that entire spectrum. So whenever you're close to maybe an unintentional transmitter, your receiver will actually suffer a lot. You don't have your own guarded band now. So that means that your noise level will basically suffer in general. And not only it will suffer, but it will basically be relatively unpredictable because you can't permit people from not being there.